Hello students, hope you all are doing well. Here in this video, we are going to take a look at another industry. It's nitric acid manufacturing industry. Nitric acid, HNO3. Let me show you the Lewis structure of nitric acid. It is having this Lewis structure, NO double and single bonds. They could get exchanged resonating. Its two resonance structures could be seen under nitric acid. Now it's a single bond, here a double bond. The minus charge goes there. Okay. Then students, nitric acid is a mineral acid with high corrosive properties. It's a strong monobasic acid. At room temperature, it's a volatile liquid. It's having its boiling point around 83 degrees of centigrade, pure nitric acid. But nitric acid water mixture, when it is concentrated nitric acid, let's say 68% of nitric acid, it's having 121 the boiling point. How could it be? Pure water's boiling point also is around 100 and this pure nitric acid's boiling point is around 83. How could it exceed both those pure liquids boiling point here, the water nitric acid mixture? It's for the reason that this water nitric acid mixtures behaves as an azeotrope. It's an azeotropic mixture with maximum boiling point. That's why. Okay. Then students, it's this pure nitric acid or aqueous nitric acid both are colorless solutions, liquids. But when you find your nitric acid bottle there in school laboratory, it would appear in either pale yellow or little bit of brown. How could it be? If it is colorless, how could it turn pale yellow? Nitric acid could go under a decomposition in a way like HNO3 decomposes into NO2, H2O and O2. When you balance that, you will find it being this. So these two are gases. O2 is colorless, but NO2 is a brown colored gas. That brown color gives a pale yellow or a little bit of brown, that nitric acid solution. When it is kept for a long time in the same bottle or when you store it for a long time, it could appear in that color. Therefore, it is more recommended that storing of nitric acid in dark bottles and at cold places. Okay students, then is that the only colored gas, NO2? Do you know other colored gases? Okay, I am going to take this as an opportunity to reveal you about the colors of all the gases. If we have few colored gases only, let me show you those colored gases, few colored gases. Then after knowing those colors of those gases, you could say that you know the colors of all the gases for the reason all the other gases are colorless. Okay, let's find them out. The colors of those gases. It's F2, Cl2, Br2 and I2 are the halogens. So, it's when you find them, it is pale yellow. It is yellowish green. It is reddish brown, let's say brown. This is a solid, but when you take vapor of that, it's purple. The solid is black in color. Then students, when you take SO3 and HCl, they are white smokes. White smokes. Then NH4Cl is a thick white smoke. It is O3 pale blue. F2O pale yellow. Then it is CrO2Cl2. We call it chromyl chloride vapor. It is brick red in color. Okay, bricks are red in color. It is brick red in color. Knowing the colors of these gases, all the others you could name as colorless. N2, N2O4, NH3, CO, CO2. NO are colorless gases. Okay, it's very easy then. Okay students, let's go back to the nitric acid, right? So, let's find it out. Why do they manufacture nitric acid? Why is that so important, manufacturing of nitric acid? I mean, let's find it out, the applications, uses of this nitric acid. Okay, if we are going to find out their applications, that for what we manufacture nitric acid. Students, when you check for the nitric acid manufacturing, it is 75% of that manufactured nitric acid is being used to manufacture fertilizers. Which fertilizers? It is ammonium nitrate fertilizers. Then remaining 25, out of that, it is 15% would be seen used to manufacture explosives. If they manufacture explosives with 15% of total nitric acid. What are the explosives? Students, could you remember this? It's we call toluene. When you treat toluene with concentrated nitric acid and concentrated sulfuric acid, there we call that the nitration mixture. You treat toluene with nitration mixture, then you get 2,4,6 trinitrotoluene. Trinitrotoluene. In short, we call it TNT. Is an explosive. Then students, further, it's this alcohol you check. It is 3 OH groups. Trihydric alcohol you have here. We call it glycerin or glycerol. When you treat this trihydric alcohol with the same reagent, the nitration mixture, if you get this being nitrated, 3 nitro groups will be added. Its students then we call trinitroglycerine. These trinitrotoluene TNT, trinitroglycerine TNT are explosives. Those are shock sensitives as well as thermal sensitives. That means when you make them vibrate or when you ignite them, those would explode. Then students, the rest of applications could be seen having this 10% would be used for all the other applications. Manufacturing of dyes, it is azole dyes are manufactured using nitric acid. Then it is synthetic fibers. What are the synthetic fibers? Those are polymers that you manufacture using nitric acid, with the support of nitric acid actually. It is when you manufacture nylon. Adipic acid is a precursor of nylon manufacturing. That adipic acid is manufactured using nitric acid. Nitric acid is used there as a reagent. Not only adipic acid but also in polyester manufacturing. The required dicarboxylic acid we call terephthalic acid is manufactured using nitric acid there. Therefore, it is important in manufacturing of synthetic fibers, means polymers. Okay. Then students, you could manufacture aqua regia. We call it boil water. So it's you would find aqua regia being used to dissolve many metals. So it's good at dissolving more metals there. So you could manufacture aqua regia mixing concentrated hydrochloric acid and concentrated nitric acid in 3:1 ratio to get this NaCl, Cl2 and H2O. A mixture of this is called aqua regia. Then nitric acid within this 10% is used to manufacture potassium nitrate, what we call saltpeter. It is used to manufacture gunpowder, saltpeter. Then further, nitric acid is used to manufacture silver nitrate. It is used in photographic fields. Silver nitrate is photosensitive substance. Okay. Then nitric acid is used as the soldering water. Soldering water. It's in soldering means welding of those metals to clean the metal surface. Nitric acid is applied. It is used. Then further, you could find nitric acid being used in some other fertilizer manufacturing like apatite fertilizers. Apatite is water insoluble substance that you could find in ores, mines. So when you treat that with nitric acid, you could make it, transform that into superphosphate, more water soluble form of that. Manufacturing apatite fertilizers, you could find nitric acid. So those are the applications. Fertilizer manufacturing, it's ammonium nitrate, then explosives, then dyes, synthetic fibers, aqua regia, potassium nitrate, silver nitrate, soldering water, apatite fertilizers, those. Nitric acid is used in those. Okay. So therefore, manufacturing of nitric acid is useful, very, very important. Next, we are going to take a look at the manufacturing process. Manufacturing process of nitric acid. Let's find it out. How they manufacture nitric acid. Okay. Then students, when you find it out, the manufacturing process, we identify this process as the Oswald process. It's after Wilhelm Oswald in 1901. He first developed this, means installed the plant as to manufacture nitric acid in large quantities using the raw materials ammonia, air and water. Nowadays we find ammonia, we take ammonia from the Haber process, ammonia manufacturing Haber process. But it was before manufacturing ammonia using Haber process, Oswald started manufacturing nitric acid using ammonia. So it was using other sources of ammonia. He found ammonia from other sources and used that on manufacturing of nitric acid. But currently, presently, we are using ammonia from Haber process. Okay, then students, it's air. There provides us O2. O2 is the active species or the gas we need there in our process, synthetic process. So in air you could find that you have 78% of nitrogen. It doesn't intervene in our reaction. So though it doesn't matter, because then what does it form would be nitric oxide. Is what we need during this process. We would be forming nitric oxide. Anyway, it's not going to intervene. So therefore, we don't find this requirement as to separate oxygen from air. We do not need to then follow a method like fractional distillation of liquefied air that we followed there in ammonia manufacturing Haber process to collect nitrogen. Straightly, we could use air as the raw material. So that raw material provides us oxygen. Oxygen we need for our reaction. Okay. Then students, it's water you would find all around. So those are the raw materials. Let's find it out how those raw materials are used in this industrial process, in the manufacturing of nitric acid. It follows 3 steps. It's a 3-step process. The first step is oxidation of ammonia into nitric oxide. This is the very first step. Then in the second step, that nitric oxide form would be further oxidized into nitrogen dioxide. In the third step, they are going to dissolve that in water as to get nitric acid. That's the plan, that's the program. That's what they follow in those 3 steps. Okay, let's go to the first step. It's the oxidation of ammonia to get nitric oxide. But before going to the first step, I need to reveal you a few things regarding ammonia. Students, ammonia is not a combustible gas. It is not a combustion support. Therefore, it won't easily react with oxygen in air. There, you need to heat ammonia with oxygen. It's, let's say, with excess oxygen. In the presence of excess oxygen, excess amount of oxygen, when you heat ammonia, it will give you N2 and H2O. It's not giving you NO, but N2 and H2O only would be giving you. It's then you need to add 6. It's, let's say, 4, 2, then it's 3. The way we balance that. These all are gases. At high temperature, H2O also is a gas. Okay. Then anyway, these products are not that important. We could have enough of N2 and H2O all around. We could find that. We don't need such a specific method, industrial method, to manufacture nitrogen and water. Therefore, it is not economically favorable products we get during this reaction. Anyway, this is not the reaction that we proceed. They are in the very first step of this nitric acid manufacturing Oswald process. Students, the only difference is here we use the catalyst platinum and rhodium. In the presence of platinum rhodium catalyst, actually it's an alloy having 10% of rhodium and 90% of platinum. When you heat that to 800 to 850 degrees of centigrade, there is an highly exothermic reaction proceeds having ammonia and oxygen in air as using them as the raw materials would give you nitric oxide. It's then you do not get you would not have N2 but NO. It's what this catalyst does. Okay. Then students, when you balance this reaction, you could find it's 4 of this being used, it's 6 of this, then it's 5 of this in the balanced chemical equation. So then it's a highly exothermic reaction. Its enthalpy change is around minus 906 kilojoules. Okay. Then while doing this, you need to mix ammonia with air. In 1:2 means with 1 part of ammonia, you need to mix 9 to 12 parts of air. It is with 1 portion of this, you need to mix 9 to 12 parts portion of air. Then you mix the ammonia and air in that ratio. Otherwise, if you mix more ammonia, it could be explosive, this reaction. To avoid having an explosive reaction, you need to maintain the ratio like this, as it is given here. Then, you need to heat these two before mixing. And you could find that your ammonia raw material could be in its liquid form. Then you need to evaporate that ammonia, liquid ammonia, by heating. It's further air. You need to heat that air and you need to compress them and mix them and send to this, pass through the catalyst. What kind of catalyst? Is that oil? Or is that something else? Is that a rod or something? No, it's not. It's a gauze. Fine gauze prepared. It's a plate-like structure. You get this catalyst being formed. Is a fine plate of platinum rhodium gauze. Okay. Then, its students, we would have many plates of such. It's 10 to 30 plates could be found in the part that you have this reaction is done. That part is called the converter. We would find that soon in our flow chart. We are going to confine these catalytic layers, those layers in the part called the converter. Thereafter, we are going to mix them in this ratio and heat them and pass through the catalytic layers. Okay, then catalytic sheets. Then it's a sudden reaction. When the mixture touches the surface, it would be exothermic fast reaction proceeding. So this high energy, thermal energy, heat it expels, could be used on some other purposes. Like that heat could be used to heat some other, means raw materials that you use. Using a heat exchanger, you would collect that heat as to heat these raw materials. We call it preheating. Raw materials would be preheated. Preheated means means while mixing, you would be mixing those heated raw materials, air and ammonia. So preheated raw materials would be sent to the catalytic layers. Then there are that exothermic, highly exothermic reaction. It's a rapid reaction, highly exothermic, would be followed. Okay. Then students, you would get this mixture of products. Then it's saying that 97% of NO would be formed. NO would be transformed into 97% efficiency. Okay. Then it's the first reaction. It's the first step that we are having there in our industry. Okay. You need to heat it up to 800 to 850 degrees of centigrade, and you need to provide this catalyst, and it is highly exothermic, and it is once to this ratio that we maintain there. It's we compress them and pass through the catalyst. That's what we do there. It's an oxidation of ammonia. We call that the conversion step. Conversion of ammonia into nitric oxide. Therefore, this chamber or this part is called the converter. Okay. Then the product mixture has to be cooled. Then the way it is cooled, you could pass that product mixture, this hot product mixture, through a heat exchanger. While it's passing through the heat exchanger, its heat would be taken by someone else. That someone else would be again these initial raw materials. So for the preheating of raw materials, that heat could be used, that you collect while it's traveling through a heat exchanger. Then this mixture would be cooled, but you need to cool it further. You need to bring it, drop its temperature to 150 around. Okay, so when you bring it 150, there would be another reaction done, as NO would react with O2, giving you NO2. Its students, again an exothermic reaction, the enthalpy change is minus 114 kilojoules per mole. Okay, so this would easily take place when you bring the temperature down. Therefore, you need to cool the mixture, and the place where this reaction is done is called the oxidation chamber. In the oxidation chamber, you give enough time those reactants, that mixture that you take here, bring here, as to get transformed into NO2. That's the step 2, second step. It's done in the oxidation chamber. Then students, next, the formed NO2 is passed to the next. Next is the absorption tower. You will find that soon. So within the in passing of that NO2 inside the absorption tower, this NO2 would start reacting with water. It is NO2 would react with water, giving you HNO3 and HNO2. This is the reaction you get there. Then this is quite unstable. HNO2 formed there is unstable. Therefore, it should decompose into HNO3 back. HNO3, it is from plus 3 to plus 5. It is an NO, plus 3 to plus 2. So it's 1 electron thing, here 2 electron. Therefore, we multiply this by 2 and it is 3 nitrogen. It is 3 of them. Then another water molecule there. Okay, that's what you get here by the decomposition of formed HNO2. So, if you multiply this one by 3, you would cancel them off. That HNO3, 3 of HNO3 with this, HNO2 with this. Okay, it's you would find a final equation thereafter as it is students, you would have 1 HNO3 with 3 HNO3, 4 HNO3. And it is 3 into 2. It's what you get is 6 of NO2. And let's write that 6 of NO2 with this 3 water and 1 water. It is 2 water. 2 of water giving you this 4 HNO3. That's what you get there. It can transform in that manner into HNO3 and it's further 2 of NO. So students, it's you could write as the next step, third step, either this reaction. It is 3 of NO2 and H2O and is giving 2 of HNO3 and NO. This is the reaction what you get there. My point, showing you these all, my point is that if you don't blindly by heart these stoichiometric ratios and those reactions, you try to get them logically, then it would be easy, it would be more easy to understand this process and you would then easily answer those questions that you could find there in the paper. Okay, so therefore students, be logical, right? When you get each step and each reaction, you get them logically. Okay, it would be very easy then to understand the whole process. Okay, let's go ahead. So, if you could write this as the step 3, it is this the step 1. This is the step 2. In the step 3, you are passing that NO2 with means through water. It's in two opposite directions we pass them. We call that the counter current method. We'll find that out in our flow chart soon. So, it's students here, what we are seeking for is the reaction that taken place there when you pass NO2 through water. Okay. So, it's you could write either this or this formed NO could be reused as here in this reaction NO is being used to form NO2, right? So, then students, it's I could add this with this as here you have NO at the product side. Here you have NO in the second step at the reactant side. My point is, this would form, this would give you some NO. That NO could be mixed with, means could react with O2 again as to give you NO2. Then that NO2 also could give you HNO3. That's the point. That's simply the point. Okay, therefore, I will add this equation with this one. Let me show you that it's this one will number it as it's the fourth one with second one. We'll add second equation with the fourth. Okay, then what you are going to have, it is 2NO going to get cancelled off. It is students, then it is 6 of NO2. Then there at the other side you are going to have 2 of NO2. Total is 4 of NO2. Okay, then it is, you have no water molecules there, it is 2 water molecules there. And it's 1 of O2 giving you there, it's only 4 HNO3. It's either this or representing whole reaction, nitric acid manufacturing, you would give it as 4NO2, 2H2O and O2 giving 4HNO3. This also you could write. Then when you give those reactions in each step, you make that sure to give this as the first step reaction with the conditions, as you would earn marks for balanced chemical equation as well as for mention of those conditions. It's not that important giving the percentages of those metals in the catalyst, but mention the catalyst and the temperature. And it's no need to by heart the enthalpy change they are taking place, but you need to know that it's highly exothermic and that energy that it expels or releases would be used again to heat those raw materials as well as for some other purposes. It's we find out they are in the industry, heating of waste as well. Okay, so then the mixture NO and O2 needs to be cooled to 150 degrees of centigrade. You need to bring that to 150. Then only the second step would be followed. That's the second one. You would earn marks for that. And 150 degrees of centigrade is very, very important. You mentioned that. Going to earn marks for that as well. Then when you mention the third step, you better, it's more safe, mentioning of these two. If you find that you can't remember this, then you logically try to reach that as NO2 with water gives you HNO3, HNO2. It is unstable, so it dissociates in this manner. So then finally you get this. Is the way that I have, you saw that, you saw me having this, dividing this, finding this, is the way we could easily get that without bypassing that. Okay, then finally this NO here formed would be reoxidized or remixed with O2 as with NO2 back. From that also you would have further HNO3. That's the idea. So those are the steps being followed in the industrial process. In each, let's say, chamber or place, site, we are going to find out what are those sites means or places done those steps. Let's find them out. We are going to draw them or state them in a flow chart. This whole industrial process. Let's find them out. There I'm going to name it as the first reaction, second reaction, and finally this whole thing I'm going to mark it as, we have not yet marked any as the third. This whole thing is the third step. Let's find them out in the flow chart. Okay. Then students, in the Oswald process, you would find the first fed is done there into the reactor or is called the converter. This is called the converter. This is the converter. To the converter we feed our raw materials. It's air and ammonia. We feed those to our converter. This converter is having those platinum gauge plates. It's 10 to 30 around. Such plates you could find here. It is platinum rhodium alloy. Rhodium platinum alloy you find in those gauges. It is the converter. So converter is having these catalyst layers. So before passing, you need to heat your raw materials. It's air you need to heat. It is liquid ammonia you would get. You need to heat it as to evaporate that. You heat your air and ammonia. For that heating purpose, the heat it produces here could be used. This is called preheating. So you need to first filter them as to remove those dust as as well as moisture that you find in these raw materials. You need to remove moisture and dust. Then you need to heat them and pump inside. It is compressing them only you pass those through the catalytic layers. So then you will find the most important product here formed is NO gas. NO gas is formed and its students you will find O2 as well remaining. So it is N2 also would remain there. Then the resultant product here is fed to the next chamber. This chamber, this is the converter. This chamber is called oxidation chamber. Oxidation chamber. Oxidation chamber. So there, you need to cool this. This is a hot mixture you pass. It is having NO and O2. So you need to cool that as it reaches 150 degrees of centigrade. So there, it would take place the second reaction. NO gas would react with O2 gas, giving you NO2 gas. So that NO2 gas here it forms is passed. You let them react for a while. So then you pass that here to the next tower. That tower is called absorption tower. Absorption tower. Absorption tower. So it is packed with an inert substance. Mostly it's quartz. Quartz is used to pack that. And we sprinkle water. We spray water slowly. It's water we spray. Water goes downward. These are gases having here. So you need to pump these gases with the pressure 5 to 10 atm pressure. You need to pump through those. So it is this water then could efficiently contact with the NO2 gas there. So would proceed that third equation means HNO3 would be formed here. That HNO3 is aqueous HNO3. So you would take that HNO3 here at the bottom of the tower. This is called absorption tower. Absorption tower. So waste gases could be collected here. Those NO that still remain could be recycled. Okay, that's what we get in the industry. This is the flow chart. So here we feed our raw materials, air and ammonia. Then after it is this catalytic layers converts that into NO. That NO is cooled. Then as it reaches 150, letting it react as to form NO2. Then we pump that NO2 under this pressure through this. It's then dissolves in water, giving us HNO3. Students, that HNO3 is having aqueous HNO3. It's you need to distillate that as to concentrate that. When you concentrate this HNO3 that you collect here, it would be maximally reach. It's as I told you, azeotropic mixture. So maximally it is 68% it reaches. So there is another step also we need to follow, but here in our syllabus that step is not mentioned. But anyway, it's you need to use concentrated sulfuric acid as to dehydrate that HNO3. Then after that treatment, that concentration process, it reaches 98, 96, 98 around the concentration of HNO3 formed there. Okay, that's the process. That's the industrial process that they use to manufacture nitric acid. Hope it's clear. Anyway, during this process, it's possible NO and NO and NO2 could be escaped, means could release to the environment, air. So could pollute air. We call them NOx. These NOx could contribute to acid rains as well as photochemical smoke. It's not only by NOx, means NO and NO2, but also by the heat it liberates. It could pollute environment. It's by hot water it liberates there. Also, environment could be polluted. What is hot water? This is dissolution of gases in water. It's an exothermic reaction. So we need to cool this towel. We need to use a water cooling system there. Therefore, it would give us hot water. So release of hot water to environment also could cause pollution there. So anyway, seeing and knowing what are the possible ways that it could pollute the environment, we need to address those issues. We need to minimize, we need to overcome that pollution it could result there by the industry, nitric acid manufacturing. Okay students, that's what we get as the process, the reactions done there during nitric acid manufacturing industry using Oswald process. Okay, it's very simple when you understand these things as just simply understanding what's having there, not by having those reactions and reactions with the stoichiometry. It's you just understand. You have three processes. First is the oxidation of ammonia in the presence of a catalyst. Then it forms nitric oxide. Then you need to clearly see the next point is the further oxidation of formed nitric oxide and into nitrogen dioxide. Then the next one is the formed nitrogen dioxide dissolution that in water. So we call those three phases having those three steps: converter, oxidation chamber and absorption tower. That's what you have. They are in the nitric acid manufacturing process. Okay, then these are actually very simple few steps and reactions that you are having there. So you need to just understand. You need to see that clearly. It's how simple it is, and you need to understand the process only. You shouldn't buy now. Then all the things could mess up. They are inside your head. Okay, students, hope you could understand these few simple points there. I have shown so far. So we are going to meet you in another industry soon in our next video. So if you are going to round up here. Okay students, goodbye.